Well, thanks for coming. So, what I'm doing today, so as you know, I like to write this down. The theme of today's first lecture is first we will review what I called yesterday ramified covers. In particular, in the one-dimensional situation, that's what the beginning will be. Say the dimension of the upstairs space of both spaces to be 1. And this will give us the description of the function field of X. So I call it the field of meromorphic functions on X. X is connected, so it's a field. And I think I will use the algebraic geometric notation here, which is C of X. So that's just notation, C of X. The round brackets remind you that quotients are allowed, right? And then, this is, so to speak, the first thing I would like to do. And then after that, I would like to discuss meromorphic functions . Concentrating on meromorphic functions because it's really easy to define them. There's no fancy business in higher dimensions. This here I restricted to 1 dimension, so meromorphic functions in higher dimensions. You still have a field of them, but geometrically they're more difficult to understand. And then I will discuss construction of meromorphic functions in a simple fashion for curves and surfaces in projective space. So for what we call subvarieties or submanifolds, primarily in our case manifolds. In projective spaces. So those are going to be the topics I'm going to talk about. Everything focused a bit on meromorphic functions. So let's get to ramified covers. So concerning the first point, so let's let X and Y be one-dimensional connected and compact. This simplifies our discussion, and of course many of the results really do require certain compactness. Now let us consider a map F, a non-constant map F, which is of course homomorphic in this context, and it is immediate fact from the open mapping theorem, and the correctness is that F is surjective and of course the identity principle says that it's finite fiber. Every fiber is finite. And yesterday I drew a picture, my favorite picture of how to do this, and it's not only mine, I think everybody draws this picture of a ramified cover. So downstairs, Y, everything's smooth here, it's not dangerous. You may have some ramification points, say it's, yesterday I had a 4-to-1 mapping, so let's take again a 4-to-1 mapping. Here you might have some ramification like this. You might have, theoretically, something like this. I never know whether my pictures exist or not. You noticed yesterday I drew a picture that didn't exist. But, so this could possibly be a ramification like this. And, well, of course, you have to have that. And so on. Let's make all 4 of these things come together here. So here we have the upstairs space where you have the vanishing of the derivative of this map, of the derivative mapping. It's a finite set because it's also locally defined as a homomorphic matrix, in this case a 1-by-1 matrix. And this upstairs set is called the ramification set. And the downstairs set, so over which it is ramified. So you see it's not ramified here, but there is a point over which it's ramified there. So that's what we count. So the image of the ramification set, in this case, 3 points. So the downstairs set, and it's easy to remember because this is the base, and therefore the downstairs set should be called B, and it's the branching set. Because I get confused with the words. So upstairs is ramification, downstairs is branch. Okay. And the degree of these, at each point, so the degree of ramification when it's not ramified is 0. The degree of when it's actually ramified, here the mapping is locally here. Z goes to Z cubed. And we say the ramification order then is 2. And the ramification order here is 1, 1, and here 3. Now we can have some fun to see whether this example exists or not. Because we proved yesterday a theorem about the order numbers. So the Riemann-Hurwitz theorem which just is proved by lifting triangles, is a very simple proof. Says that the topological order number downstairs, which just as vertices minus edges plus faces of a triangulation, is the same. Let me write it. This is degree. So degree in this case is 4, and in general I'll call it B. So it multiplies. And then you make a mistake that you have to correct. So this is D. This is not the differential of this. This is D times that. And you make the mistake, and the mistake is the total degree of the ramification.
Should it be either way around? X and Y?
Probably. Thank you. Yeah. Degree.
I mean, then you're mapping.
Yeah. Degree. Yeah, of course. Degree. Yeah. My psychology is I compute upstairs by computing downstairs. Thank you very much. There must be something that happens in my brain that I reverse things. I mean, it's just terrible. Thank you. So I start from my point of view downstairs, and I lift everything, and everything gets multiplied by D, except I make a mistake, and if you compute carefully, you just subtract off the degree of the ramification. So we know that, we discussed this in detail yesterday, this is 2 minus 2 times the genus of X. Genus being the only topological invariant of x. And this is d times 2 minus 2 times the genus of y. And minus, in this case, let's look at it, whatever it is. What did I get? Let's see, 2, 3, 4, 7. I did it again. Okay, but now I want a possible example. Okay, and now I had, instead of 3, I have here 2. So I think, so 2, 4, 6. Okay?
Can you guarantee such a map?
No. No, that's a very interesting, I can't guarantee anything. And that's, we talked about this yesterday, right? It's not at all clear. And that's a very interesting question. And also, it's not at all clear where these ramification points go. You see, some points are, you have maybe if you choose ahead of time how many points, 3 points on y, and you say you want to build this thing over it, maybe you can, and then you move the 3 points. I don't know, maybe then you can't build it. You see what I'm saying? It may depend on the points. There may be all sorts of things going on. We will talk about it. Okay, finally I get an example that theoretically could exist. Okay, that is the review of ramified covers. This is a beautiful theory. And now, all of you have courses, and usually these courses are very boring in mathematics. But here is one of the main reasons for field extension theory. So, let's look at what we might call the function field extensions. What I'm going to explain was known to Riemann and Weierstrass. I think what I'm going to explain, I'm not sure, maybe it's the theorem of Weierstrass or Riemann, I'm not sure. And then was one of the motivations to really understand, for example, Galois theory. So we have, the reason I write x over y is that you have a function field downstairs, y, and you have a function field upstairs, x, field of meromorphic functions. And of course, if you have a function on y, you can lift it to x. This is stupid. I mean, you just regard a function on y as a function on x. So you regard this, and I think the notation usually is without an arrow, as a function field extension. C of x is a function field extension of the functions on y. Yeah. Okay, why not? And now we want to understand this function field, so the goal is understand this thing here. Okay, so understanding this means understanding the functions on C of x which are not in C of y. Do you get it? I mean, that means you have, I'm not claiming I can understand C of y, but at least I can understand the extension from C of y to C of x. Okay. So I take a function, meromorphic, in C of x. And I'm thinking, so that's an optimistic statement that I'm thinking. I'm thinking that it's not in C of y. And I want to understand what's going on. Let us go to this picture. So let me do it in red up here. So f is red, so f is upstairs. So it's a function upstairs. And it has a value here, a value here, a value here, and a value here. A priori 4 different values. Right? And if I move these values, it has a value here, value here, a value here. So on each little piece here, it has a value. So each little piece is bihomomorphically equivalent to something downstairs. So you can regard it as being a function down here, but having different values up here. Okay. Now those values, I say, you see, I learned much mathematics from physicists. I'm completely optimistic about this situation. I just write down the first thing, and then the second thing, value, and the third value, and the fourth value. Now there's no such thing as the first value, the second value, the third value, and the fourth, but I don't care. I just write it down because it's blackboard and it's chalk. So I say value 1, say I'm at this point here, value 1, let's be a little rough, the value 1 of f, value 2 of f, value 3 of f, and value 4 of f. Those are the 4 values upstairs. In fact, if you allow me to forget the rest of this stuff, I have 4 disks up there. And I will call them the first disk, the second disk, and the third disk, and the fourth disk. I mean, you will call something differently. Because you come from Calcutta, probably there you have some other system of calling things. But there's no problem. But those values on each of those disks are holomorphic functions, right? Or meromorphic functions. Let's not worry about poles right now. Holomorphic, it's the same thing. So, I want to write down something that is well defined that is not well defined. Right? The first thing you do is be unafraid of everything in mathematics. Just write it down, be completely unafraid, and then say that's of course nonsense, but then fix it. Right? So the first thing I write down is a polynomial, which is well defined. A polynomial, say, of some indeterminate, let's call it zeta. So this is some indeterminate. In this case, 4 variables, so let's write it down. Zeta minus W1. Okay, I still go about zeta minus W2. Yeah. Zeta, this is indeterminate. You see, we learn very quickly that stuff like polynomials gives us a way of writing down something that is well defined. This polynomial doesn't depend on the order of the w's, right? I make a permutation. I mean, it's pretty stupid. I make a permutation of the order. It doesn't change this. This is stupid, but fundamental. I know many of my friends who don't understand this right, so think about this carefully. And this is zeta to the 4th. You even notice that it is what we call a monic polynomial in zeta. And I don't know your notation, but maybe your notation is the first symmetric function in the W1 to W4, zeta cubed, plus the second elementary symmetric function, these values, minus and so on. Right? The symmetric functions are generators of the invariance of the permutation group. right? They are the primitive generators of it, and so they appear here as we need. Now notice several points. This polynomial is well defined. It is locally well defined, obviously locally well defined here, because I don't have any, I said that it's homomorphic at these points. If I have poles, you have to watch out a little bit. And going to the ramification, you can check very easily that everything continues. So this polynomial is a polynomial zeta to the fourth times, let's say, a coefficient 1 of f zeta cubed plus coefficient 2 of f zeta. These various coefficients, maybe, I don't know, some systematic way would be better. What I'm writing here is probably not particularly good. Coefficient 4 of this polynomials. And then I ask you, what are the coefficients? The coefficients are functions, because these things are varying, not just numbers. If I took the 4 numbers here, then I would get a number, but as I vary the point, I get different numbers. So these are meromorphic functions on the base. So these are meromorphic functions. Ci of f is a meromorphic function on the base. I proved the theorem. Given a function upstairs, it satisfies a monic polynomial of degree at most d, where d is the degree of this mapping. I've shown that the upstairs field is an algebraic extension of the downstairs field of at most degree d. Right? Do I need to repeat that? I hope you see that the reason these algebraic techniques were developed is there are problems of other subjects. For example, field extensions of meromorphic functions where they're useful. So that says that this extension, c of x over y, is an algebraic extension, and the degree of c of x over y is less than or equal to d. Right? And you know from your course with Mr. Penkoff, or somebody's course, or in kindergarten, that if you take something of maximal degree, you're smart. Because you see, if you take something of maximal degree, then you have an intermediate field by associating just that function and its various powers. But you know the degree formula because it says the degree of the big extension is the product of the degrees in between. So, and you can fool around and there are all sorts of abracadabras, so with primitive element and all of this stuff, but it says that c of x is c of y extended by a certain function. I shouldn't call it f because it might not be f. Let me call it g. Yeah? Maximal degree. That's a beautiful theorem. It's an obvious theorem. It's only what you can get here on the fibers. That's it. I think the theorem of Weierstrass. You see, Weierstrass was in Berlin, and another mathematician in Berlin was Kummer. And Berlin was very good at those times, Kummer, algebraic thinking mathematician. But it's very, 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 very interesting that Runge was a student in that group of Weierstrass, Kummer. So here are these two pure mathematicians. Runge is an applied mathematician. You should read his works on applied physics. It's unbelievable. I mean, really phenomenological studies of things. And of course, you know the Runge theorem of approximation and so on. So very fundamental approximation theorems and mathematical. But that's the way it was in those days, you see. That people knew mathematics and not just focused on some one thing. In particular, as it's becoming nowadays, applied mathematics requires serious pure mathematics. It's not just fiddling around with something. Jung is a perfect example in the old days. But this is in this group, Weierstrass, Kummer. I'm almost sure you should take a look if you're interested in history, I think. Okay. Of course, it was Emmy Noether and Emil Artin and such people who really wrote down the field extension theory carefully. And it's a rather new thing. Artin's notes are some of the first good lecture notes on the subject. Okay. Everybody understands that, but nobody listens. Well, let's do a special case. See, I didn't say anything what CY is. Maybe this is nothing. Maybe it's a joke here. Right? So, maybe it's a joke. So, let's talk about what C of Y or what is C of X. So, let's take the special case. Y equals P1. C. Well, in that case, F, maybe I should not use the same letter. Let's say, so I don't know, maybe I will, let me use the same big letter. F is just a meromorphic function on X. Do you understand? You see, if you have X and this map F to P1, I said to you yesterday, it is a fundamental thing that you regard a function as a ramified cover. Okay? So now I'm just talking about, this is just a function, and I'm discussing this as a ramified cover over P1. And so what I'm interested in is the field extension C of X over the field extension of over P1. And P1 is, well, we know what it is, but I'm going to write it down. P1 of C, and if you allow me to use the coordinate Z, it's the rational functions in Z. So you pull back the rational functions in Z, and you get functions here, and you want to know what you have. Notice that this is a pure transcendental extension of the complex numbers. So this is a pure transcendental extension. The transcendental degree of this extension is stupid. Here it is. There's nothing algebraic. It's purely transcendental. Is 1. Okay, so you're looking at this thing as an extension of a pure transcendental thing. Well, here's the F. Let's take F to be of maximal degree somehow. In this, maybe not F. Here's some meromorphic function, and now let's take G to be maximal degree in this ramified cover, and so it says that this is an algebraic extension of this. Yes, this corresponds with this notation here. So we have this given meromorphic function. Then after giving that, we find one of maximal degree, so-called primitive element, and you have this. Okay. So algebraic function field of transcendence degree 1 with the extension bounded. If you take F original with minimal degree with extension degree. Hey, Kane, it's really impressive that you made this.
I just hate it. Like, I think something like train got delayed, train got cancelled would happen every morning.
Yeah, well, of course today it's, and this is.
I woke up for nothing. I woke up to wait in the train station for 40 minutes.
We were really impressed. This guy, first of all, this is really impressive. It's so impressive that I'm going to repeat a little bit so you don't miss out on anything.
Thank you.
It's nice to have you here. So much of what I've said so far is a review. So I talked about reviewing ramified covers and the Riemann-Hurwitz formula. So, and I actually put an example here that works. And now what I wanted to point out, and that's that's where I've just more or less finished now, is if you have something like this, then we can regard the field upstairs as an extension of the field downstairs. I can just lift functions into the field upstairs, and I'm interested in studying this extension. Okay. And I explained that if you have a function upstairs, so this is a function upstairs, then what you do is you just look at its values along this ramified cover. Here I have 4 values along this ramified cover, and of course, if I'm not careful, I just call this the first sheet, second sheet, third sheet, fourth sheet. That's not well defined. But here, and its values here, if I write that down, somebody tells me that that's not well defined. But if I write down a polynomial, putting these values in here, right? Then that polynomial is well defined because the coefficients are just the symmetric functions in those numbers. And that polynomial is good because when I put in f, it kills it. So this is a monic polynomial that of degree at most 4, degree 4, that kills this function. May not be the minimal polynomial, maybe wasn't careful or something, but now we apply field theory. And all we have here then is that the extension here is, the degree of the extension is at most the degree of the map, and it's an extension over the base field of an algebraic extension by one function, so you just choose a function of maximal degree, and it's an algebraic extension of that. That's all I've said. And I applied it to the case where the downstairs is P1, so we have the extension of the full field on P1, which is just the rational functions, and this is of this degree. So I think got you more or less up to date. It's a beautiful, I like it very much because it's an example of how thinking algebraically about field theory helps you think about this. Now, I would like to discuss higher dimensions, and meromorphic functions in higher dimensions. Let's recall the definition. You have X, and you have a covering, and you have, on each covering, you have a pair of functions. So that's the data. And of course, we're thinking about these functions as defining a quotient. And so you don't want G to be anywhere identically 0. And in fact, you can take these things on this set. It's a theorem, but you can prove that these functions are locally prime, so relatively prime at any point in the set UI. Now, I need to talk about what that really means. Okay. We talked about yesterday. Holomorphic function has a 0, then it doesn't have any zeros in the neighborhood. The same thing for the denominator. If it has a 0, it doesn't, and then you could cancel. So you can either assume that it has a pole, so that's when the denominator is bigger, the order is bigger, and you cancel that, so the denominator is 0, the numerator is not 0, and vice versa. Pole is 0. Okay, so that's what it means. You take these things relatively prime. You can't cancel them anymore. Okay. So that's a little bit more delicate here. Let's talk about it for a while, of course without proof at this stage of the game. So maybe U alpha, so the first remark is we can always shrink U alpha. U alpha may be shrunk to our convenience. But that doesn't help necessarily. Situation looks like this. Let me give you an example of a situation. This maybe is the zero set of let's say I'll write in colors. The pink set is the zero set of U alpha. Now, you see it has two components. That's what I meant to do. I have to make this precise sometime, what it means, two irreducible components. You have to really discuss this whole matter. I mean, I'm not discussing it precisely, okay, but it has two components. Okay. So, that's U alpha. Now, I have to read this. Now G alpha is also the same type. I mean, it has several components and all sorts of stuff. So what can happen here is G alpha could have, by the way, you know what could happen here. This thing could have a multiplicity of 17 here along this component. You have to define that. By the way, here's how you define it. This component, I used the wrong, well, it's almost pink. This component has singularities maybe here, but you prove a theorem that the singularity set is small. So you move away from the singularity set, and you see that this is here away from the singularity set. This set is at least a one codimensional complex manifold, and you take a disk transversal to that, restrict the holomorphic function to that disk, and it should have a zero of order 17. Let me say it again. You have a bad set where this thing is, and these things can be bad. But you prove the first theorem is this set, if you can remove a set of codimension 1, which is called the singularity set of it. Okay? You can move away from that, and then you take a transversal disk. The map is still singular because that has a multiplicity maybe there. You look at the transversal disk, you restrict to the transversal disk. This is a function of one complex variable, and the order of vanishing is 17. So this has an order of vanishing 17. That's great. Then you go over here, and this other thing, this is even smooth there, but I don't like it here because these things intersect, so I go away, put a disk here, and this has an order of 18. Now we're dealing with the meromorphic function M alpha, which we're thinking F alpha over G alpha. Right? So we better understand the G alpha. Well, the first thing we do, we look at G alpha. We're incredibly lucky. G alpha vanishes nowhere generically. You see, through here it's vanishing at some of the same points where F alpha vanishes. But generically it doesn't. So that we're incredibly happy about that. It vanishes at order 28 here. Okay? Again, my numbers probably won't, no, I think here the numbers are always automatically, I can find something wrong. Yeah, but the thing is, what goes wrong here is that where this thing it vanishes of order 17, this guy also vanishes. And maybe it vanishes of order 92. Okay? And furthermore, we really have to localize this discussion and make sure everything is good, so we may have to shrink this picture to prove anything here. But I'm not shrinking, I'm just saying it's okay like it is. So, okay, so what are we going to do? You see, this F alpha, it's a unique factorization domain. So F alpha factors into P alpha 1, and P alpha 2. And P alpha is prime, so it's P alpha to the 17. My God. So, how do I do this? Oh, I don't know. Okay, P alpha 1 and P alpha 2. How many components do I have? 2? Right? This one's 17 and this one's 18. So in a unique factorization domain, you can factor things into it's just like the integers. You can write a prime decomposition of that thing. And these prime decompositions correspond to the zero sets and their multiplicities. Okay? That's the way F alpha looks. And now G alpha, let's look at it. G alpha, well, aha. The first, this is 17. This one's good. So it's the same one to the 92. And then we only have 2 of them. That's great. So P, the third one, P, which is prime, alpha 3, the third one here, to the 28. So that's what you do. You prove you can do that, and everything's relative to a prime at every point if you cancel. So I'm not going to cancel. So what we're going to do now, don't forget we're looking at this ratio. So this ratio is equal then to, if I do this right, to P alpha 2 to the 18 divided by P alpha 1 to the 92 minus 17 is 55, I hope. No, 65. No, 75. I'm getting there, 75 maybe, right? 92 minus 17 is 75, is that right? And do I cancel anything else? No. P alpha 3, 28. So you see you have zeros and poles, they're one-dimensional, and you cancel, they're relatively prime, nothing upstairs occurs downstairs. It's just like in dimension 1, but it's not so simple, it's not just Z. It's all these complicated prime divisors, and you see immediately that you're going to have to do some algebra here. Okay? So I'm just telling you the truth, and then later we will do some algebra. And studying the algebra amounts to studying the local theory of holomorphic functions in higher dimensions. And if the ambient space is singular, then it's even much more interesting. Okay. Okay, so that's the deal. And now we want to take an example, which is, after all of this fancy business, let's take an example of a meromorphic function, which is meromorphic on a function on C2. The most stupid function you can think of. So let's say I have 2 variables, m of z and w. Just naively, this is something you can think of at the beginning of mathematics. Euclid could have thought of this. Right? Z divided by w. No, Euclid would have trouble because, as you know, symbols it was difficult. My understanding is the Arabic cultures really, because of, for various reasons, brought symbols into, good use of symbols into mathematics. So I don't know whether Euclid could write Z over W or not. Okay. So this is good. Here's the complex plane. This is z-axis. Z-axis. And this is w-axis. Well, let's see what happens here. let's restrict this function to the z-axis. The z-axis is where w is 0. I learned this from my grandchildren. You know, is where w is 0. So here w is 0, and it's 0 in the neighborhood, and that's the denominator. So from my point of view, this thing is identically 0, infinity, because it's infinity along there. Okay, looks great. Let's restrict it to the w-axis. Well, as you see, w-axis means z is identically 0, so here the whole thing is 0. And there's a problem there, but let's not worry about it. The function is identically 0. Now already, you're really beginning to worry. I always like to write dangerous points in red. Because somehow or another there's a fire burning here that we have to understand. Because here it's 0, and here it's infinity, and here it's 0. Well, it's even worse than that. If you have a line here, which is z equals lambda w. So now these other lines, lambda is neither 0 nor infinity, so it's easy to say what it is. So m restricted, let's call this the line L lambda. Z is equal, restricted to the line, m restricted to the line L lambda. If I'm lucky, I am lucky, I think it's identical to lambda. Right, because it's lambda, right, it's identical to lambda. So, the value at this red point is very, very mysterious. Okay? So, the first thing is a notation, classical notation. That red point is called the indeterminacy set of the Ramified function. So the red point, after we divide it out so these things are relatively prime, the indeterminacy set of the function is where these things both vanish. Here, I'm assuming that we've already divided out, so there's no common divisor here. So already divided out at each point. So this is really relatively prime at each point. So that's the indeterminacy set. And here, in this case, here, this is, in this example, the indeterminacy set of M is just the origin. Okay? Now, the first remark here in general is, I think we owe this remark to Carl Stein, is probably in the 1930s, also early after the war, with his student Reinhold Bremer, is you write down, no, Stein asked this question. You look at this thing, and the point is you look at this thing and you say, I'm going completely crazy. It has all, yeah? So then you have the courage to ask the stupid question, which is a very good question, is what is the value of a function? You see, you never asked that question. You maybe asked it in third grade when you're, right? And then you were confused appropriately because your teacher told you some stuff. But you really want, what is the value of a function? Particularly in this case. And what you learn is that the value of a function is a set. So here, what is the value? Okay, so the value of m, let's say at the point 3/16. Well, here you're extremely happy. So you say it's 3/16. Well, you say, okay, let's make sure, I'll just say it's the set 3/16, just to make sure, because I'm a little bit worried about this. Then I say, what does the value say here at some place like there? And at something like w equal to 0, so 7, 0. Well, then you invent a new point, which you call infinity, and we even make it precise because we know infinity is something in the Riemann sphere. And then you say, what is the value of m at 0? Right? And in the original discussion, you were fed up with me because I told you it's indeterminate. And it has, well, okay, here, along this line it is 0, along this line it is lambda, along this line it is infinity, or I don't know, whatever it is. But look at what it is. It ranges from 0 to infinity. It takes on all values, does it not? Right? I mean, it takes on every value for every possible value of lambda. If you don't mind, I will not write it lambda. I will write this thing as the line is z0, z. So I'll write this line. Don't forget, it's a one-dimensional subspace of C2, so it's a point in projective space, right? And so I will write it, the line, depending on the point in projective space, is, well, let's just write it. I don't care. It's that line, whatever it is. It's equal to C times this point. Right? So I'm even much more precise now. This line, I'm bringing in some good structure here. This is C times this point Z0, Z1, where Z0 here, this is the whole line, and this is the point Z0, Z1. Okay, so as this point, as the line varies, it takes on all values. Now to be precise, I guess it takes on the value Z0 divided by Z1. So, well, what is P1? Now, let's be precise about that. You need to check something here, and you can, that if you're a maniac, and you don't go here along the line, and you go to 0 in some completely insane way, you will still only get values in P1. Okay? If you get limiting values, you will get limiting values only in P1. Okay? So in reality, you can all possible well-defined limiting values you can write in P1. It is a set valued mapping, which is generally speaking point value. But at the bad points, you really do get a set of values. Okay? You started a little bit late here, so move on.
Professor, then it means the definition of meromorphic function is different in the one-dimensional case and higher dimensional.
Completely. The definition looks very much the same locally, these things,
Yeah,
but the
because
geometry.
in one-dimensional space, we usually say the meromorphic function is that except the set of discrete poles, the function is holomorphic.
It's a holomorphic mapping to P1.
Yeah, but here at this case, like 0 is more like essential. It's like essential singularity. Right?
Yes, and I'm happy you say that because this is a very good remark, Vicente. Thank you. So let's recall the function theory of one variable. The three types of singularities. You know, of course, this removable. It's not singular at all. Pole. Okay, that just looks like 1 over z to the k. Or essential. Okay. This singularity here is not essential in that sense. Let me explain why. Let me remind you, well, let me just emphasize what I just said. The set of values that is taken on here in this limiting sense, okay, is compared to the ambient space, very small, and is a compact manifold. I mean, it's P1. As you know, let's go through the big Picard theorem again. In a neighborhood of a central singularity, in one complex variable, every value, except for maybe 2 or something, is taken on every value is taken on infinitely many times. Not only that, that's a deep theorem. Maybe, I don't know if you've seen the proof, but the easy theorem that you know probably is Qaisar-Weierstrass theorem. It says that the image of any small disk around a central singularity is dense. Here, well, as a map to P1 is subjective, but it's somehow a very small set compared to the dimension of the ambient space. Okay, so your remark is terrific, Sintao. I like it very much. But you need to always keep asking this question: what's the difference between this and essential singularity? And I will now try to answer your question. Let me try to answer your question in an honest way. That was just blah blah. Let me try to answer it in an honest way. Okay? So the correct viewpoint here, at least from my point of view, and this viewpoint was understood really not that long ago and emphasized in research results of Reinhold Remmer and Stein and people of this time in the mid-50s. Is a meromorphic function in the sense we're talking about here, Sintao, so geometrically in terms of values and so on, is a graph. It is not just some blah blah quotient of things like that. It is a graph. So it's a graph in x, whatever x is, times P1. So, okay. So let's discuss this matter. X and P1. Let me discuss it in this example, and then we will come to your Sintao's remark about essential singularities. Okay? Let's discuss this graph in this example. Okay? The graph, I'm going to write it down now in pictures and in equations. Okay. So you see, if you have the point 316, 316, yeah, right? This is now, my granddaughter's 11 years old and she's learning this in school. So you go over here to the point 3/16. Oh, that's 3/16, so let's write it as 3/16. You don't mind, right? It's the same, because it's the quotient. Okay, that means that this point is in the graph. Right? And now what was some other stuff? Aha. So we go over here to 7,0. Now I don't remember what is infinity. Well, it has to be the same. It's fantastic, it's the same thing. So 7,0 goes to the point, this is the identity map actually. It goes to the point 7,0, which of course is 7 divided by 0. Right? Now, any point except for the origin is good. Oh, I didn't draw the picture. It goes here. here. 7, 0. Now just for fun, let's say that the origin is here. 0, 0. Okay. Well, here's wonderful. It's wonderful. This is wonderful. This is the graph. It's just like a graph of a function for the stock market. You see, you should go to a bank and tell them that you're looking at a neuromorphic function and it's a graph of development of a hedge fund. And they will pay you $1 million a year to start, and then if you're big time, you get $1 billion. None of this mathematics here, this stuff, but they use graphs. Then you should say that unfortunately, hedge funds blow up. So what happens here at 0? Yes, that's tomorrow for the bank. Well, let me just look at the space of all possible values over 0. Okay. What's going on here with this graph is it gets everywhere danced along here. It's very hard to draw, but I'm going to make some statements that will help you understand it. I mean, I'm just that's nothing what I just said, but that, okay? And now Remote's definition of a meromorphic function or a meromorphic mapping is that a meromorphic mapping from something to something else, you see, then you become abstract, is a graph, let's say a meromorphic mapping F, is a graph which is contained in the product space. And of course you have the projections onto the pre-image and image. And this graph is an analytic set. This is locally defined by equations, holomorphic equations. So locally defined, and this is where Santel's question is going to come in, by holomorphic equations. That's what it is. It's a graph that despite the stock market going bananas at time 0, 0, this set here is going to be locally defined. I'm going to define it in a minute by algebraic equations in algebraic geometry or analytic equations. So it is a graph, and there's one condition. Stein calls this thing, I can't remember, this hat and this mapping, this hat, these are two projections. Maybe I've got the hats wrong, I don't remember. This is a half arrow because this thing is not everywhere defined because of indeterminacy, as the usual mapping, but it's defined as a set value mapping. So if you wish, the value of f at x is, you go upstairs and go downstairs. That's what you do, my granddaughter does in 11 years old. The value, you go to the graph and you go over here. But here, the value, you go to the graph, it's everything. So the value is, in that sense, everything. But it's defined by equations. Okay? So it's defined by equations. And the condition is that this mapping, let me just say, this mapping should be proper and bi-holomorphic outside of the set of codimension 2. So a small set, a set of codimension 2. Okay. Now let me do this for you now, Santel, and then let's do something with an essential singularity and see what happens, okay? So here, in mapping, in the example, the graph of M, okay, is the set So the first variable is x, so of, say, ZW, Z0, W0. So you see, in C2 times P1, see? Now I have to tell you, the statement is that Z over W equals Z0 over W0, so I'll write it ZW0, I have to write it this way, minus W, okay, so I use, these are the coordinates in C2, so I maybe should use something better, but, okay, Z over W equals Z0 over W0, it's probably, what do I do? Yeah, okay, ZW0 plus WZ0, this is not too bad to make it, equals 0. I've just written down the equation. Now, come on. This equation is the most stupid equation you could think of. Right? I mean, it's a quadratic equation. Right? It's the most simple-minded quadratic you can think of. If you check it, it defines a submanifold of P1 cross, of X cross, C2 cross P1. And now look at the projection. Let's look at this projection on the C2. So in my notation up here is M dot to C2. And I told you what we have to look what happens at the origin because they're very interesting. So let's look at M upside down hat inverse of the origin. So what I'm doing is I'm taking this thing and I'm making a projection onto the ZW, and now I'm looking at what everything goes to what everything here goes to 0. So I'm putting 0 into this equation. All right? So if this thing is equal to 0, then I put 0 into this equation, so I have 0 times W0 minus W times 0 times Z is 0. I have no equation. The equation vanishes. Okay? So it says that the pre-image is just a copy of P1. It sits in the graph in a beautiful way. This is a beautiful submanifold. Couldn't be better. It couldn't be better. By the way, let's talk about this. Is called the blow-up, rightfully so, if you think of the stock market. It's called the blow-up of the origin in C2. Why is that? Because, well, above the origin you have a copy of P1, and you see what happens. There are what you call it, artistic pieces of art where you've seen this. Because if you have a line downstairs, you can lift it here and get a line here. But what happens? You see a line downstairs has really an image, a value here. So the line downstairs goes to some value up here, real value. So it goes up here. And what happens is you have these different lines. It goes to different values. Do you see? So downstairs these lines are spinning around here, but upstairs, as you spin, it raises. I can't draw the picture, but you see what I mean? Well, I could draw it. It's like this. Upstairs, so downstairs we have things like this. Upstairs we have things like this. That one's there, that one's there. I don't know, something like this. You see spinning? Okay. So we blow up the origin depending on the angle of these lines going through here. It is just a reasonable, very nice global equation that defines all this. This couldn't be any better. Okay. And now let's take a centile example. If you take the example of well, I don't know what the example is. Yeah, okay, so yeah, I know. Let me write it here and then I will call it quits for this morning. But it is a beautiful question. I really like your question. Let's take your favorite essential singularity. So f of z complex plane, I will define to be e to the minus 1, I always have a Gaussian in my head. I'm sorry, I come from probability theory. But I have, you should, well, I put the Gaussian, this is the behavior of the Gaussian at infinity, right? Because the variable is 1 over z. So you think the Gaussian is terrific, everybody in statistics thinks it's wonderful. But if you do it in complex, you see in the neighborhood of infinity is a horrible essential singularity, right? It's only when you go to the real axis, life gets nice, okay? So I made infinity equal to 0. And you see that you would require, here's C, and here's P1, and here's, say, 0. Okay? Now, outside here, it's okay, it's the same thing. And in here, it's okay. So, now you're right on the money. In here, it's just some sort of wild, I don't know, the limits is everything. By the way, in some horrible way, because I mean, the behavior here is incredible. However, you will never define that graph with an equation. You will never define that graph. You just try, it's an interesting exercise. That you just take this set that's defined, it's just this set, all limits you get. You will never define it by an equation. Here, you will define it by a stupid algebraic equation. So in some sense, the singularity here is small, and the singularity here is huge. Okay? That's about the best I can do right now. But over the 2 weeks, you will get a better feel. So let's meet this afternoon. Let's hope it's better. I see a guy walking with no stress. And I have a question to ask. Could we meet a little bit early this afternoon? Is there any obstruction to that?
When this time?
So it's 5:15, at 3:15 instead of 3:45? Would that be okay?
Yeah, it's okay for me.
Is that okay?
You should
Latif,
send
is that
out an
okay
email.
for you? It's not okay for you. When's okay for you? 3:30? Okay, 3:30.